Hello and welcome. My name is Jennifer Shaw. Today I will present to you my newest paper about superadiabatic combustion of hydrogen air and hydrogen N2O mixtures, published in Combustion and Flame. In this video, I'm going to define superadiabacity, talk about superadiabacity of hydrogen-oxygen flames, show the importance of NOx chemistry, show some results, explain the heat release of hydrogen air, and present some major findings of this paper. All the simulations are done in Cantera 2.6 via a Python interface. Superadiabacity is defined as the local temperature overshoot over the adiabatic temperature. This graph shows the equilibrium temperature in blue and the superadiabatic temperature or TSA in orange. We can see that the maximum temperature in the beginning drops down to the equilibrium temperature in the end of the domain. This paper of Leo and Gilder is the basis of my research, since they show that hydrogen-oxygen flames do not show superadiabacity. The difference between their and my results is that the NOx chemistry is not included. And we have found that only when including NOx chemistry the phenomena can be observed. Here we see some 1D flame simulations with and without NOx chemistry. As I said before, only when including the NOx chemistry, we can see the phenomena. As we see on the left, without NOx chemistry, the predictions of the flame temperature are constant from the beginning till the end of the domain. While on the right, when including NOx chemistry, the graph has a maximum temperature and then drops down to equilibrium temperature. Now we see some simulations. We see here the two different mechanisms, first without and then with NOx, and we start the simulations without NOx. Then we have our initial conditions and our two oxidizers, air and N2O. The results are the following, that we have a constant equilibrium temperature. When we now change our mechanisms to including NOx and keeping all the other conditions the same, we see the results as a maximum temperature going down towards equilibrium temperature. Next, we see 0D simulations in a homogeneous batch reactor. It is to mention that all the simulations have been done with 3 different mechanisms to show the difference between the mechanisms. All results are showing similar results. Here we only show one mechanism. On the left, we can see the results from hydrogen air, and on the right, the hydrogen N2O mixtures. We can see that there is a big difference between the two oxidizers. While the maximum temperature of air is not much higher than equilibrium temperature on the left, and it then slowly decreases to equilibrium temperature, the results on the right for N2O show a big spike in the beginning and then a fast drop to equilibrium temperature. When we now track our simulations, we first define our reactor, then we have our initial conditions and the two oxidizers, air and N2O. We start with air. Then we have the following result, a small peak and then slow down to equilibrium. Oxidizer N2O. We have the following results, a big spike in the beginning and then going down fast to equilibrium temperature. Here we see the heat release simulations with a 0D batch reactor. In green we can see the total heat release, and then in blue and orange the major reactions based on the post-ignition region. It has been established in many papers that the endothermicity is inducing superadiabacity. Basically, heat is released very quickly and increases the temperature in the flame. Then the endothermicity brings down the temperature in the flame to equilibrium temperature. On the right, we can see the results from Leo and Gilder. The top shows the relation of negative heat release and the reduction of flame temperature. On the bottom, we can see that there is no negative heat release region and therefore also no superadiabacity can be observed in hydrogen-oxygen flames. This relates back to the inclusion of NOx chemistry, and that only when NOx chemistry is included, TSA can be observed. In our case, the reaction which induces negative heat release is the N2 dissociation reaction in blue. The reaction goes in the reverse direction, meaning N2 is split into N plus NO. The activation energy here is very large, which leads to the slow endothermic reaction and TSA. Now we show the simulations. In the beginning, we have the definition of our batch reactor again, including heat release. Then we have our initial conditions, our oxidizer, and then the selection of our reactions, and here is the result. The major findings of this paper is that superadiabacity can only be observed when NOx chemistry is included. We also see different order of magnitude for superadiabacity for the different oxidizers, air and N2O. Also, the reason for the superadiabacity is different for the two oxidizers. Thank you very much for listening.